And then we have a student of 10A, Ru Peng Shen, who dealt with D equals 3 for 1/2. That's the critical mass between 1/2 and 1. So we're dealing with D equals 3, S of C equals 1/2, and D equals 5, and S of C equals 3. So it's supercritical. And because we don't have a conserved quantity, we assume that we have an upper bound on our norms. So. If we have an upper bound for all time on the critical norm, then we have photons and scattering, and this is equivalent, as was seen in Monica's talk on Monday, to the scattering size being finite. So I'll just write it as where in D equals 3, S of I, and D equals 5. And a brief check would show that these are also scale invariant quantities. So I suppose the first thing to say is, why do we care about such a thing? I mean, okay, so you assume something to be true. Great. Why is that? Why care? And I've gone myself. I'll admit I've gone back and forth on this issue of whether it's relevant or not to assume a bound. But in this case, I suppose I've come to the conclusion that it is, probably because I did this paper. But there's two issues that need to be pointed out with this, or perhaps more than two. That you have this in the defocusing case, or in the focusing case rather, you have an ODE, which you can use, which is going to blow up in finite time. And so you can use this ODE, along with finite propagation speed to construct a blow-up solution in the focusing case. But the critical norm blows up, along with that. So we know that. So what we're ruling out here is what's called type 2 blow-up, which is where the critical norm stays bounded, but you still have blow-up in scattering size. And there's been a number of work, including very recently, or maybe a week ago, there was a paper showing that type 2 blow-up does occur sometimes. So we have a result of Krieger and Schlag and Tataru for the wave equation showing a focusing type 2 blow-up. And then recently, Merrill and Raphael and Rodiansky showed type 2 blow-up for a D greater than or equal to 11 and an energy supercritical for the NLS. So, for the NLS. So it's not such a obvious thing that you never have type 2 blow-up. And we're just in the process of gradually proving all these different theorems for all the possible cases that might arise. And Merrill and Zog prove that if you have a blow-up of the critical norms, I believe it was for D equals 3, then the blow-up has to be in a self-similar way. So you can't just have any old blow-up of the H half norm that you like. And so that perhaps that could be used to somehow then show that the H1, not rule out the H1 half norm blows up because it has to blow up in a specific way. So that would be an interesting problem, I think. Okay, so at this point I will describe the concentration compactness method in a bit of brief explanation. And I realized last night while I was writing this that I had to give you a literature lesson, perhaps. So the quote, what a tangled web we weave when first we practice to the seed. Most people think that's Shakespeare. It's not. It was Sir Walter Scott who said that. So anyway, that's the applicable thing for the concentration compactness method, right? Like that's how the method works. I mean, it really is. So you know that you have global abundance and scattering for small data. And Monica talked about this. And then you also have some kind of perturbation theory. So if you have small perturbation of a solution that scatters, then you're going to have scattering. And so therefore there has to be a minimal energy or mass or what have you solution that blows up, if it ever blows up. So then you say, okay, well, what if I have such a solution? And if you have such a solution, and Mike Crisp mentioned this in his talk, yesterday, he basically said you have to have everybody working together, right? So, like yesterday when we played soccer, and there was even teams like this interacting, nothing. But usually when there's even teams, you have to have someone. And it's the same idea as in this problem. You have to have all your solutions working together. They can't be somehow divided and all doing their own thing. And therefore, of course, then they have to be in a single weight package is what it boils down to. And this is by now a pretty standard argument. And so we have the upshot of all this. No, it's, no, because as NFT goes to zero, that means the position gets more and more spread out, right? So we have to, if NFT goes to zero, we have to pull it back together to get it to be a compact set. That means it's very spread out. Yeah. Yeah. If we're going up, see, so this is H2 here. Yeah. Yeah. And so the point is we use the double duomotic to gain a half of a derivative. In fact, you can gain a whole derivative here, but then it would cancel around that zone. Yeah, so if you look on this compact set here, you see that that's exactly what you would, that's the most that you that's within a constant of the optimal improvement. Because your solution, because of your scaling, your solution has to lie in a compact set. And so then you bulk your, so this is optimal improvement. And so this was actually the beginning of our collaboration, because I was giving a talk in the student seminar on the double duomo set, and so this is something I'll write down the people who have been involved in this. And so we have these 3 papers here on the NLS math critical, using the in and out decomposition. But I think you can also do the same argument with the double duomo set. So anyway, so I'll write it like that. And then you have this paper with the energy table, and then boost, and field for the show and extend, so the weight, and then tau, and myself for the KGV equation. So this is a method for the double duomotic, which has proved to be quite useful in a number of papers. And so I presented this in the student seminar at UC Berkeley of this method you can use to solve all these problems. And I mainly concentrated on the KEV and then also the energy table problem, where they show that you can get L2 regularity, the ideal quantity theory of L2. And so Andrew Lowry said, well, does this method work? You could have higher regularity as well. I said, yeah, I mean, there's 3 papers here that you can use to get up to H1. And he said, well, we should talk about this. And so he said, like, can you get H2 with the wave equation? And I said, well, it's radio poly. And so we talked about it. So that's the advice, I guess, I have to talk to the student seminar, because you can help people learn, and you also get something out of it yourself, probably too. So, yeah. So you're freaking today. Oh, okay. Oh, thank you. Yeah, sure. Yeah, so I'll write it over here. Okay. So the idea of that is as follows for the wave equation. So we let the T, and we want to show that this lies in our space, whatever that might be, and so we take a inner product. And we know that V of T equals wherever you want, you can greater than T in one direction, less than T in the other, and then you integrate that. And what's nice is that you take, this should be T1. As you take T naught, heading off to the input of your interval, then this term is, because V of T naught is compact, in a compact sense, you know, it's going to convert weakly to 0 in your critical. In your critical, now you can use, you have to use some, Fourier truncation or bulk taxi. I prefer to use integrating with a C0 infinity function as opposed to delta function, because we didn't want to lose our final propagation. So instead of taking a Fourier truncation, we just modify it slightly. Deal with that, we don't want to lose. The final propagation speed comes up in a very way, because so you have these terms go to 0 weakly, and so therefore you're left with just these terms in your inner product. But now look, you have an extra derivative that you've gained. So that's where you can jump from, say 3 halves to 5 halves. And so you're left with this integral. calculating this stuff. It's fun. And at that point, you have to do a little linear algebra. Do a little linear algebra and say, well, if and so that's just the general fact, and then we want to choose our A's and D's appropriately. So we choose our A's, that gives us a good Shukar type form, and then our D's, that gives us when the inner product happens, then you get a good bounce. So the B's, we use the Sharp-Huygens principle. So we so we take the interior like see it. We're coming to the inner product in here. So C is greater than and so we have this we're integrating these C's and well, but by the Sharp-Huygens principle, so you can always take this inner product. This is that. And put it out here, right? It puts it out here, so that inner product is actually going to be 0. Now, I'm glossing over the thing, because if you're taking a half derivative or whatever, even it's a non-local operator. But the point is that this kind of heuristic still works if you take your frequencies, truncations carefully, and things like that. You can do it. But a point remains that you can do the same trick for the NLS, where you don't have Sharp-Huygens, right? So you don't necessarily need Sharp-Huygens, although it's certainly nice to say something 0, right? It goes away then. So then you're left with the rest. And the rest you can use the radial sublimit method. So UQ for X. So in radial theta we have this radial embedding in any dimension. So no, you don't have it in 3 dimensions, but you can. There's ways to work around it. So, you don't need all of it. Is the point, because you're showing that this ST is bounded by U 1 over T squared. Right, so the ST, the critical numbers, is bounded in. And so then when you integrate this so when you're taking it's just a sigma norm. Then this is bounded by n of t, n tau, which gives you a full gain of regularity, right? You gain the full derivative, because you have the 1 over derivative minus the plus in front. So you picked up the derivative from there. So you gain a full derivative at the n of t when you have in 5 dimensions. In 3 dimensions, you can't quite do that because you don't quite have this you don't quite have this embedding here in 3 dimensions because it fails, but so you can work around it though, and as long as you're content to not go all the way up to 3 halves, but you really don't need to go all the way to 3 halves. So you can gain this regularity here, and then once you've done that, then